All right, grade 12, here we go. After learning about charges and electrostatic forces with Coulomb's law, the next part here is we're going to talk about electric fields, and we're going to try to relate the field force of electrostatic forces with gravitational forces, which are both fields, forces that emanate through space. Okay, so the overview of what we're going to do here in this lesson is first we're going to define and compare electric fields with gravitational fields. Then we're going to learn how to draw electric fields. And the last thing we're going to do is a basic calculation where we use electric fields to calculate force and acceleration of charged particles. All right, so if you did a quick search and you wanted to find out what electric fields are and watch some Khan Academy videos or whatnot, you would find pictures that look like this. You have a charged object with a bunch of arrows coming out of it. You have negatively charged objects with arrows pointing towards it. And then if you have combinations of charges, you get these interesting maps that also have similarities to magnetic fields that we would have encountered in grade 10. So they kind of have these similar patterns of stuff you've seen before. And then you would see an equation for electric fields where E with a bar on it represents the electric field. K is Coulomb's law, or Coulomb's constant. And this looks a lot like Coulomb's law, but it's missing something. It's missing a Q over here. And this R, don't worry about that R for now. That's a vector thing. All right, so we would just be looking at something like that. We're going to explore that formula in a bit. And then here, if I had multiple charges in a system, how would they work together to create an electric field in space? Okay, so all charged objects, such as this one or that one, emanate electrostatic forces throughout space. Okay, and as we learned in the last episode here, F equals K, Q1, Q2 over R squared is Coulomb's law. So any charged object, such as that positive charged object, okay, I would if I had a positive charged object in space, I would consider that as Q1. And any other small positive charge that I put over here, which I would call Q2 in that equation, would experience some type of force. And if they're the same charge, that little small charge would experience a repulsive force. Okay, that would be pushing it away, or both of these objects would be pushing away from each other. Okay, so every charged object will emanate a force throughout space. Now this other little object over here, that test charge, this little test charge over here could be much further away, okay? It could actually be in an infinite distance away, and it would still feel a force. Now, if it was infinite, it would feel a very, very small force. But the closer they get towards each other, the greater that force is going to be. Okay, so the unique thing about field forces is they don't have to be in contact. The force is felt through space. Okay, so knowing that, the electric field around an object is the region of space around a charged object for which a positive test charge would experience an attractive or repulsive force. So if you take a look at that little statement here, you would see this term positive test charge. That appears everywhere. The only way we can detect an electric field, so if I drew a box and we're somewhere deep in outer space, okay, and I want to see, is there an electric field over there? What I would have to do is I'd have to bring a small positive test charge and then press play on the simulation and see where that positive test charge goes, okay? If it stays still and doesn't move, then I would say there is no electric field whatsoever. But if we see that positive test object start to go down and accelerate over time, then we would say that yes, there is an electric field presence and there must be another positive charge somewhere in space. It could be a very far distance away, but there's a positive charge in space that is exerting a force on my test charge, okay? So physicists have defined that fields relate to a positive test charge, a small positive charge that we can put in space so that we can track and map what the charges are in space and how they're emanating a field around them, okay? For example, if I had a negative charge over here, okay, that positive test charge, instead of moving that way, would move towards the negative charge, okay? And then I'll be able to start tracking what these fields look like and mapping things out, okay? So let's erase this for a second. So just to summarize again, the electric field is a region of space around a charged object. So if I set up a Van der Graaf generator and I created a positive charge on the Van der Graaf generator somehow, probably by induction, okay, the electric field is let's draw this in a different color. It's the region of space around that positive charge for which a small little positive test charge is going to experience a force. So if I place that test charge over here, okay, I'm just going to do that. If I place that positive test charge over here, it would experience a force and move in that direction. If I placed it over here, it would experience a force and move in that direction. If I placed a positive test charge over here, it would also experience a force and move in that direction. In fact, that force would be experienced to a very far distance. Okay, so all that region of space around that center is an electric field. Okay, so definition of electric field strength. We understand how to describe what an electric field is, but how do we explain the strength of it? So the electric field strength is the ratio of force experienced by this charge, the force experienced by that positive test charge, divided by its charge. It's a ratio, okay, around that object. So if I brought this little test charge closer, the force is going to be a lot greater. Okay, so then I would say that the electric field strength here is going to be greater than it is over here. Okay, and let's try to see if there's a formula for that. So according to the definition, it's the force. So force, and I can say force is equal to K Q1 Q2 over R squared. That's Coulomb's law. So it's the ratio of force per unit charge of my test charge. This is the charge of the source. That would be that charge, Q1. And this is Q2. All right. So it's going to be the force per unit charge of my test charge. So I got to move that over. So to describe my electric field strength, which is symbolized like that, that's my electric field, it's going to be equal to the force per charge of that test charge, which is going to be equal to K Q1 over R squared. So if I wanted to calculate the electric field strength, okay, let's just draw another one of these Van de Graaff generators. Okay, if I wanted to calculate the field strength over here at a distance of 1 meter away and over here at a distance of 2 meters away, okay, all this formula is telling me is I need to know K, which is 8.99 times 10 to the 9, times whatever the charge of this object is. The greater the charge, the stronger the field is going to be. So let's just imagine that that is positive 1 coulomb. Let's say this is positive 1 coulomb. Okay, and then divided by whatever distance I'm looking at. So at this point, at 1 meter, I would have 1 meter squared, and that would tell me that I would have, wow, a whopping 8.99 times 10 to the 9 newtons per coulomb of force per charge. That's my electric field strength at that position over here. If it was 2 meters away, I would substitute a 2 in here, and then I would take that number and divide it by 4. It'd be smaller. So we can see that the strength rapidly drops off as we're moving further and further away. If I wanted to draw a graph of that, my electric field strength, okay, and R, it would look something like that, okay, where I rapidly drop in electric field strength as I move further away because it's an inverse squared function. Okay, so that's our electric field. So the electric field would be a region of space around a charged object, and at specific points, the actual strength of it is the ratio of the force experienced per unit charge, the force experienced per unit charge of whatever this little test charge is going to be at that point, okay, which can be calculated by K constant times the charge of the central object divided by that distance. Okay, and the unique thing is at that point over here in space, every object will experience this field strength. So every object at 1 meter is going to experience 8.99 times 10 to the 9 newtons per coulomb. Okay, but the actual force that it experiences will be different because I would have to multiply that. Okay, and that is similar to gravitational fields, and I'll show you why. Okay, so gravitational fields have the same format. Okay, all matter. So if I have a planet which has a mass, all matter emanates gravitational forces through space. So if I had a small, a speck of dust over here, that dust is going to experience attractive force according to Newton's law of gravitation, okay, which looks very similar to the electrostatic Coulomb's law, okay? And doesn't matter where I am. If that dust is somewhere over here, I mean, the force will be smaller, but it still experiences an attractive force. Now for gravity, it's always attractive. So that force will always pull that dust particle towards that planet and slowly accelerate it. Okay. Now for the strength at that position, if I wanted to know what the field strength is, well, what's the definition? Well, the gravitational field strength is the same. It's the force per unit mass. Okay, so the gravitational field strength at that position is equal to the force per unit mass at that position. Okay, that's what it says over here. The gravitational fields are region of space around an object of mass where a small test mass would experience an attractive force. And then the field strength, okay, which we're going to see is actually g, the acceleration of gravity, is the ratio of the force experienced per unit mass of a small test mass in that region of space. Now, what was I talking about here as g? So if I go back to this formula g m1 m2 over r squared, if I want to convert that into my gravitational field strength, I'm going to take this and make it F over m2 is equal to g m1 over r squared, okay? And y is F over m2 equal to g, okay? Our acceleration of gravity. That's because F equals m times g is equal to the force of gravity, if you remember from what we did at the beginning of last year. F equals m times g is the force of gravity. If I divide m over here, F over m is equal to g, the acceleration of gravity. And I can calculate the acceleration of gravity on any planet as long as I know g, which is 6.67 times 10 to the minus 11. And if I know the mass of the planet, and I know the radius of the planet, I'll be able to then calculate g whatever planet. So we can go back and calculate the gravitational field strength at a position on the surface of a different planet, such as Mars, okay, or Venus. We would use this formula, which is g, okay? So it's the same thing. It's the ratio of force per unit mass, whereas electrostatic fields or electric fields is force per unit charge. So it's very similar. And you have these formulas in your data booklet, okay? So let's see how we draw electric fields. Well, all we do is, here's my central charged object, and the electric fields are represented by arrows showing the direction that a positive test charge would take in that position. So as I showed you before, if I put a positive test charge over here, that positive test charge would fly in that direction. Okay, if I put a positive test charge here, it would fly in that direction. If I put a positive test charge here, it would fly in that direction, and so on and so on. So if I really wanted to map out what the electric field around this central object would be, I would keep putting positive test charges all around here and drawing the arrows, and eventually it would end up looking like this. This is a drawing of what the electric field would look like around a positive object, where these are the positive test charges flying, and you can see it's very symmetrical. If it was around a negative object, the positive test charges would fly towards the center, and so that's why the arrows are pointing to the center. And then if I had two different objects in space, positive and negative, well, these arrows are showing what's going to happen to a positive test charge. At first, it wants to fly in that direction, but it's also being attracted in that direction towards the negative charge. That's why it makes a bend towards it. Okay, if I was right in the middle, it goes right towards it. And this looks like a map between a positive and a negative charge. Okay, so just to show you how I would draw this in reality, if it was on a test, if they gave me a positive center object and they say draw the electric field, I just have to make sure that I draw arrows to represent that the field is symmetrical. It's even on all sides. Okay, and the arrow sizes should be roughly the same. If it was a negative object, I would do the other way. That's the positive charges will be attracted towards that negative object. And I'll try to make it symmetrical. Okay, and then you can see here, if I had a negative charged object here and a positive charged object, well then you'd get these curvy arrows that looks something like that. Okay, now what would happen if I had two positive charged objects? If I had two positive charged objects, okay, and I have a positive test charge here, it would be pushed out that way, but as it gets closer to this electric field, that electric field is going to repel it, okay, so that positive test charge is going to end up flying in that direction. This positive test charge would end up flying in that direction. Okay, so if I just remove these, I remove these positive test charges and just draw these arrows. Okay, we can say that at this region in space, right in the middle, a positive test charge would experience no charge because they would cancel out. Okay, so I can trap stuff in the middle there. So those are three different drawings of electric fields around charged objects. Now, the last thing we're going to do is look at basic calculations with electric fields. Okay, so how do I use the force? Let's go back and say I calculated the electric field strength by plugging the numbers into this formula. And at a specific place around this object, I found that that is 1,000 newtons of force experienced per coulomb of charge. Okay, so that's what's happening over here. An electron is placed in an electric field with 1,000 newtons per coulomb magnitude. Calculate the force experienced by the electron. Well, that way I can say that the electric field is equal to 1,000 newtons per coulomb. Okay, so how would I calculate the actual force that it's experiencing? Well, the charge of an electron is equal to 1.6 times 10 to the minus 19 coulombs. And an electric field was the force experienced per unit charge is equal to 1,000 newtons per coulomb. So if I wanted to find the force, all I would have to do is multiply 1,000 newtons per coulomb by whatever the charge of that object is going to be. In that case, it's going to be the charge of an electron. So the force is going to be equal to 1,000 newtons per coulomb times 1.6 times 10 to the minus 19 coulombs. The force is going to be 1.6 times 10 to the negative 16 newtons. Okay, that's how much force that would be experiencing, and it would be negative, which means it's attractive. And then the last thing we're going to look at here is how to calculate the acceleration using that force. Well, if I have that force, and then I apply Newton's second law, F equals ma. Okay, so the acceleration would be the force divided by m, which is equal to a. So negative 1.6 times 10 to the negative 16 newtons divided by the mass of an electron, which is 9.11 times 10 to the minus 31 kilograms, should give me the acceleration. Okay, and I just have to plug that into my calculator. I'm not going to do that right now, but I just showed you the method of how I would apply electric fields and calculations. We're going to do another video where I'll do about 4 different practice problems with electric fields to get you guys used to the calculations, both calculating the strength of it and then using it in force calculations. And then we're going to make a video of electric fields in plates.